In this video, we will look at Euler's method, which is a numeric way of approximating the solution of a linear equation. We start by the introduction, which is essentially that the vast majority of first-order initial value differential equations cannot be solved analytically, meaning we can't just find a solution by putting our pen to paper. So the linear, separable, and exact equations we have seen in previous videos are the main exceptions. And while it is true, we also did qualitative graphs of solutions without having to solve the equations, which was quite impressive. But sometimes we need quantitative data, and that's where we go to numerical methods such as Euler's method. So we will go through Euler's method, step through some examples. We will start by looking at an example to introduce Euler's method. So we have dy dt equals 3 minus 2t minus 1/2 y. You can see this is a linear differential equation, and it can be solved because it's linear using integrating factors. And we will solve this both by using integrating factors and Euler's method as our first example. We will start to get a feel for what Euler's method is doing by looking at the graph of some of our solutions to this equation. So you can see if we start and we follow, say, this line here, this equation, we start somewhere near the y-axis. We initially increase, we kind of flatten out before we start decreasing again. So what you notice is even where we don't necessarily have the solution pointed out, we're kind of interpolating and finding this curve. So you can also observe that many tangent lines at successive values of t almost touch, and that's where we use our imagination to consider starting a point on the y-axis and then linking the segments to complete the curve. And we produce a piecewise linear graph. And such a graph, this graph here, would be an approximation to the solution of the differential equation. And this is the idea behind Euler's method. We're going to just kind of solve for little pieces at a time, and then we kind of imagine that we can piece them together to make a solution curve. We want to consider how we can use tangent lines to approximate the solution y equals phi of t of the initial problem near t equals t naught. So we know the solution passes through this initial point, t naught, y naught, and from the differential equation we can find the slope, which is f of t naught, y naught. Thus, we can write down the equation of the tangent line as y equals y naught plus f of t naught, y naught, t minus t0. Again, here is our slope. So the tangent line is a good approximation to the actual solution curve on an interval short enough so that the slope of the solution does not change appreciably from its value at the initial point. Thus, if t1 is close enough to t naught, we can then approximate phi of t1 by y1 is equal to y naught plus our slope times t minus t naught. And then essentially what we do is repeat this process. So unfortunately, we don't know the value of phi of t naught of the solution at t1, and the best we can do is approximate using the value y1. So we construct a line through t1, y1 with the slope f of t1, y1, and here's our line. And then essentially, to approximate the next point, we use the last y1 point and the last slope over here. And continuing in this manner, we get that y is going to be equal to yn plus f of tn yn t minus tn. Hence, this is our approximation for the next line. Y sub n plus 1 is equal to yn plus f of tn yn tn plus 1 minus tn. And I moved everything up a little so I can have more space, but essentially to get our next point, we start with our previous point, and then we multiply by the change, which is the slope times the change in time. Again, this is just a standard equation of a line. Now, we're also going to use fn is equal to tn yn, so we can express this equation as yn plus 1 is equal to yn plus fn, this should be a times tn plus 1 minus tn. Finally, if we assume there's a uniform step size h between the points, which is quite common, we obtain Eulers Formula, which is yn plus 1 is equal to yn plus fnh. In this way, using this formula, we're going to generate a sequence of values, y1, y2, y3, that approximate the values of the solution at point t1, t2, t3. So we're just approximating solutions at particular points, t1, t2, t3. If instead we need of a sequence of points, we need a function, then we create the piecewise linear function constructed from the collection of tangent line segments that we've been finding here. That is, let y be given. If we're looking at the portion of the graph between t0 and t1, we take our equation over here for the line, y equals yn plus f of tn yn times t minus tn with n equals 0. With n equals 0, again, that gives us the line between t0 and t1. For t1 and t2, we take the same equation, but now we take n equals 1, and so on. So we'll get a myriad of line segments and for each interval, and by concatenating them, we get our function. And I've moved up all these points here so that we can start this example. So we have dy dt equals 3 minus 2t minus 1 half y, and y0 equals 1. This is the example that I had shown you the graph of. We're going to use Euler's method with step size h equals 0.2 to find approximate values of the solution of the initial value problem at yn plus 1 is equal to yn plus fn times tn minus 1 minus tn. And we're going to use t equals 0.2, 0.4, 0.6, 0.8, and 1 because h is equal to 0.2. We are going to compare the values we get with the corresponding values of the actual solution. And since we need the actual solution, we will start by solving this equation analytically. Here's my equation rewritten. 0.05yt plus dy dt equals 3 minus 2t. And actually, I rewrote it one more time in this kind of form that you would expect if it's separable or exact, which is our m now is going to be 0.4 y of t minus 3 plus 2t, and then whatever's in front of the dy dt is our ny, so it's only 1. So here, obviously, well, not obviously, but it's certainly not separable because m is a function of both y and t. If it were separable, it needs to be a function of just t. And it's not exact because if you recall, to be exact, the derivative of m with respect to y has to be equal to the derivative of n with respect to n. And here, since n is equal to 1, the derivative is going to be 0. And here, if you take the derivative, you're going to get something other than 0. So we know it's not exact. But I can look at this again, and I can see that this is in the form of dy dt plus p of t y of t equals g of t. In other words, I can rewrite this, and I can see that it's linear. And actually, if I looked at this more carefully, probably the first thing I should have tried was linear, because obviously the y, or not obviously, I shouldn't say that, but because the y isn't squared, it's not to a negative power, it's not sine of y or e to the y, it's just plain y, it is a linear equation. And actually, I didn't start with linear just because I wanted a word to talk about why it's not separable, not exact. So it is a linear equation, and then we will use our integrating factor. So the integrating factor is equal to e raised to the minus 1/2, that's our p, our function p, dt. So that's going to be e to the minus t over 2. We will multiply our equation, the entire equation, by our integrating factor, so from here to here. And then we are going to integrate both sides of the equation with respect to t. This side of the equation we need to use integration by parts. And over here we just remember that our integrating factor was chosen so that the integral of this would just be e to the integrating factor times y of t. Over here I've integrated the other side using integration by parts, and my solution is y of t is equal to 14 minus 14t plus c e raised to the negative t over 2. Using my initial value, y0 equals 1, I plug in 0 for t, and my value 1 is going to be equal to, here I get 0, here I get c, 14 plus c, so c is equal to negative 13. So my solution for the initial value problem is going to be 14 minus 4t minus 13e raised to the negative t over 2. Now it is time to look at Euler's method. So I'm just going to write a few things down. First, y0 is equal to 1. That comes from our initial value. Our values for t, we start at t naught equals 0, and then our step size is 0.2. So t1 is going to equal to 0.2, t2 is going to equal to 0.4, etc. Looking for my equation for y, it's up here. I have it in my notes of Euler's method, but I also went ahead and I copied that down here just for quick reference. So when I want the next iteration of my y term, then I'm going to use this formula. If I want to approximate the tangent line at the point that I'm at, I'm going to use this formula over here, up here. And I copied it down here for reference. Now that I have y naught, and that's from my initial condition, I want to find y1. And again, I'm going to use this formula here. So n is equal to 0. So according to my formula, with n equals 0, I have y1 is equal to y0 plus f of 0 times h. So first I'm going to look at f of 0. So f of 0 is when t is t naught, and then y is equal to y naught. So t naught is equal to 0. And y naught is equal to 1. So then that will equal to f, plugging in for f. Where's f? Here, my differential equation. I have 3 minus 2 times t naught, which is 0, minus 1/2 times y naught, which is equal to 1. And that will be equal to 2.5. Now, if I want the equation of my tangent line near t0, I'm going to use this equation here. So y is going to equal to y naught, which again is 1 by my initial condition, plus f naught, which I've just calculated here, 2.5 times t, where's my equation, t minus tn. So t minus and t naught is 0, so I have 1 plus 2.5 times t. Now doing my next point, I want y2, so I'm going to use this formula with n equals 1. So y2 is going to equal to y1 plus f1, which is, and plugs in t1, y1 times h. So f1, t1 then is going to be equal to 0.2, because I'm incrementing. And then my y1 I get from my equation here is 1.5. I plug that into my equation, and my n1 is 1.85. The rest I would just plug into an Excel sheet, but I did put for n equals 2, n equals 3, n equals 4, the tangent lines near t equals 0.4, 0.6, and 0.8. I kept over here the solution we got when we solved this equation analytically, and I computed y.2 and y.4 just so I can compare. So if we look at, if we look at, 0.2. For y at 0.2, we get 1.5, and over here we get 1.85. So you can see the approximation is close, but not that close. And just a note, one way to achieve more accurate results is to use a smaller step size. And I moved our calculations up here for reference, but what I have is the table for comparison of the exact solution with the solutions we get using Euler's method. So here's several step sizes. This one is the one we were using 0.2, but then we get down to a very small step size. So when t equals 0, 1, 2, 3, 4, 5, you can see as h gets really small, well, this one's exact because we just start with the initial condition, but here we're looking for 2.11, and you can see that as h gets really small, going this direction, we get closer and closer to 2.11. The other thing we can see is the approximations become more accurate as t increases. So even just looking through here we kind of have a large error of 0.1, but by the time we come over here, our error is down to the second decimal place. Our next example is dy dt is equal to 4 minus t plus 2y, where y naught is equal to 1. We're going to use Euler's method with several steps to find approximate values of solutions for t between 0 and 5 and compare them with the corresponding values of the actual solution. Here you can see I identified the differential equation as linear and solved using an integrating factor. Also over here I had to use integration by parts, and I got my solution as y equals minus 7/4 plus 1/2 t plus c e to the 2t. And then plugging in my initial condition y naught equals 1, I get y equals minus 7/4 plus 1/2 t plus 11/4 e to the 2t. I moved my solution up here for reference, as well as a couple of solutions at y1 and y2. After I looked at this problem, I realized trying to get to y1 and y2 was like really overly ambitious. It was like a fool. I thought I was just going to calculate all these things because remember, we're starting at y equals 0, and you want decently small step sizes, which suggests if we went to y2 with this step size, we would need 20 of them. And here I solved for, well, y naught is given to us. I solved for y1 and y2, and it's not like it's a lot of calculation, but it's more than I want to do. So the things I am going to mention is I am going to do y1, I'll do a few calculations, and then the rest I did on Excel. And then the other thing I could have done, instead of going to y1, I could have done something like y5, and maybe my step size would have been 0.2. But think about it, like they suggest going from 0 to 5, so you probably don't want to do 5 with the really small step sizes, unless you're going to program it, or as I said, put it in Excel. I copied down my formulas here. Just for quick reference, my f of n, again, is my dy dt. Just to remind myself, I'm plugging in tn and y into 4 minus t plus 2y. So my f naught then is going to be t naught y naught, which is f of 0, 1, because my t naught is 0, and my y naught, my initial condition, where is it, is here, is equal to 1. So that will give me 4 minus t is 0, plus 2 times y, which is 1, is equal to 6. Now I'm going to plug in to my formula here, y of n plus 1, so n is equal to 0. So y1 will equal to y0 plus f naught times h, and h is 0.1. So I have my 1, my y naught, my f naught, which I just calculated as 6, and my 0.1 is my h, and I get 1.6. To calculate my next point, y2, I start with f1, plugging in t1 and y1. So t1 is 0.1, y1 we just calculated is equal to 4 minus t plus 2y is equal to 7.1. I can plug that now into my formula for y2 is equal to y1 plus f1 times 0.01. So I have my 1.6, my f1, my h, and I get 2.13. I don't think you really wanted to watch me calculate the other values, but I didn't want to calculate them by hand this way either. So I put this in an Excel spreadsheet. These are the answers I got. And I did want to see as I approach, so I did worked out the last F9 and Y10 here so that I can compare. For Y10, I get 15.7. And again, Y10 is with my T10 is equal to 1. So now I can compare these two values, and they're not that close. But I suppose compared to the infinity of the number line, I suppose they're sort of close. And this is the idea of how to do Euler's method. As I had commented in the last slide, the approximation wasn't that close. It was actually closer for our first our first example. So we're going to look at a couple of notes with regard to that. Here we just have the kind of a quick summary of the Euler's method where we have this formula, we use it repeatedly, the result of each step we use to execute the next step, and then we generate a sequence of values, which we saw in the previous slide. So here's our approximation to the first problem we did, and here's a graph, an approximation to the second differential equation problem we did. This one, the solutions weren't quite as close. And what you want to recall is that when you have a first-order differential equation, you have infinitely many solutions because of that arbitrary constant c. And then the initial condition picks out one member of the infinite family by determining the value of c. So at the first step, Euler's method uses the tangent line approximate to the graph y equals phi of t, passing through the point t naught y naught, and this produces the approximate value y1 at t1. So the second step, we don't have an exact point as we did with the initial condition, so we're really just using a nearby solution, phi1 of t, that passes through the point t1, y1, and etc. for each subsequent step. So the quality of the approximation, this is the main point, the quality of the approximation after many steps depends strongly on the behavior of the set of solutions that passes through the point tn, yn. So what I mean by that, in our first example, the general solution is equal to y equals 14 minus 4t minus ce to the negative t over 2. The initial value sets c equals to negative 13. So the family of solutions is a converging family, since this term here, our minus ce to the minus t over 2, the term involving the arbitrary constant approaches 0 as t approaches infinity. Since all the solutions are getting close to each other as t approaches infinity, it does not matter very much which solutions we are approximating by the tangent using Euler's method. On the other hand, the second differential equation has a general solution y equals, this should be positive, 7/4 plus 1/2 t plus c e to the 2t. And this is what's important. Because the term involving the arbitrary constant, that's c e to the 2t, grows without bounds as t approaches infinity, this is a diverging family of solutions. So we expect errors in this example to be larger than those in the first example. So a member of a diverging family of solutions will always be harder to approximate than a member of a converging family. To summarize this video, we talked about Euler's method, which is a numerical method we use to solve or approximate a differential equation where we cannot use analytical means to solve the differential equations, and qualitative solutions or graphs is not sufficient. So we went over the method of Euler's method, and then we also talked about the quality of the approximation after many steps depends strongly on the behavior of the set of solutions that passes through the points, and a member of a diverging family of solutions will always be harder to approximate than a member of a converging family. And I should also mention another way of getting better approximations is to have a smaller step size h. And that's it for this video. Thank you for watching.